Okay, now let's talk about the algorithm. The algorithm is called the branch and bound algorithm for solving integer programs. Let's use the example we just gave you. X1, okay, 15 over 4 and 9 over 4 is LR optimal. Unfortunately, rounding up or down both fail to find the optimal solution. Okay? Note that rounding up or down simply means to add two constraints, one of these two. If you want to round up, that means you restrict your x1 to be equal to 4. Okay? You restrict your feasible region to this red section. Or if you add x1 equals 3, that means you are restricting yourself here. In any case, you really eliminate the possibility of finding the optimal solution, or you eliminate too many feasible points. So instead of adding equalities, let's be somewhat more conservative. Let's add inequalities. Okay, I'm going to add either x1 greater than or equal to 4 or x1 less than or equal to 3. In that case, when I do this, I'm going to consider this region. And when I do that, I'm going to consider another region here. Okay, that means I split my original feasible region into two sets. And then I want to solve these two sets one by one, and then compare the outcome. Okay, we're going to branch this problem into two subproblems, one with an additional constraint. This strategy obviously will work because here there is no feasible solution, right? No IP feasible solution because everything here is fractional. So when I do this branching, or when I split the feasible region to two parts, I am sure that I will still find an optimal solution because I did not eliminate any feasible solution. Okay, so that's the idea. So technically, if we add x1 less than or equal to 3, we solve another LP like this. Okay, very easy. You can very easily here, this is an optimal solution. Or if we add x1 greater than or equal to 4, we solve another LP, and optimal solution is here. And then what I want to do is to compare an optimal solution here and here. And eventually, one of them will give me an optimal solution. You probably have one question. This guy seems to be an integer point, but this is not, right? So in this case, I cannot simply stop here. For the second region, I need to apply the same strategy again, and again, until I really get an integer solution. Okay, let's see how to do this. So when we solve the linear relaxation and find any variable violating an integer constraint, just like the second region I showed to you, we will branch this problem again into two problems, one with an additional constraint. Okay, and in any time when we do this, we will always get linear programs, and each linear program can always be solved simply with graphs or with linear simplex method or whatever. And once we solve a linear program, if the LR optimal solution is IP feasible, then it becomes a candidate. Later we will compare all those candidates and choose the best one. Or if any of them results in a variable violating the integer constraint, we will simply recursively branch on that variable, and so on until we can solve all the IP problems, all the relaxations. Okay? Given a fractional solution branch. For each linear program, for each subprogram, basically recursively solve that problem. That's branch and bound. So let's give you the whole idea with the following example. I'm going to give you all the details that you need to have for branch and bound. We want to solve this problem. Okay, maximize 3x1 plus x2, subject to that 4x1 plus 2x2 must be no greater than 11. Graphically, it's here. Okay, the constraint is here, and you have some feasible points. It's very easy to see that an optimal solution is here. Okay, IP optimal solution is here. But let's see how to use branch and bound to solve it. First, we solve the linear relaxation. Okay, so we simply do the linear relaxation. An optimal solution is here. This is fractional. Okay, x1 is fractional. So we need to branch on x1. Now I'm going to add some constraints for x1. The branch and bound algorithm typically can be depicted with a branch and bound tree or a branching tree. Each node represents a subproblem, like here. This is our original problem, the relaxation of our original problem. Okay, optimal solution is here, and we also want to record its z value. Okay, currently 33/4. Each time that we branch on a variable, we create two child nodes by adding two additional constraints. Okay, once we add a constraint, we focus on one side of that original problem, and then we try to solve it and keep moving. For example, when we add x1 less than or equal to 2, okay, then we're going to consider another linear program with two linear constraints here, okay, 1 and 2. Okay, and then again, this can be solved. Okay, an optimal solution is here. So later we will need to branch on x2 because x2 is fractional. But before we do that, let's try to solve P3. P3 is the outcome of adding another constraint called x1 is greater than or equal to 3. In this case, when you have this LP, this problem is infeasible. Okay, and that means we do not need to consider this node anymore because this node do not give us any candidate solution. Okay, or graphically, you can say the left-hand side part contains an optimal solution, and indeed that's true because above this line there is no feasible points. Okay, so organizing what we have so far, the original LR can be solved with a fractional x1. So we branch on x1. Here, we know we need to do something else because x2 is fractional. Here, this problem is infeasible, and we say this node is dead. We don't need to worry anymore about this node. Before we move on, note that z2, okay, here, is less than z1. What does that mean? When we move down one level further, we decrease our objective value. Now, remember that we are working with a maximization problem. Why do we see that z2 is smaller? It's simply because that we are adding one constraint. For any LP, if you add one constraint, you know you're not going to do better, and typically you do worse. This is an example that you do worse because you add one constraint. So in general, when we branch to the next level, the objective value associated with the subproblem will always be weakly lower. For a maximization problem, we will always do worse, and the objective value will become smaller. This will be useful later. Okay, anyway, here, this guy is fractional. Let's try to branch subproblem 2 on x2. Now this is 1.5. So I'm going to add two constraints. either x2 less than or equal to 1 or x2 greater than or equal to 2. When we add this constraint x2 less than or equal to 1, what's going to happen? The feasible region is here. It's here. And once you solve the linear program, an optimal solution is here. This is integer. Good. So now we get a candidate. Okay, we get a candidate. Also, when we add another constraint x2 greater than or equal to 2, okay, now we have 3 constraints. We get this triangle as our feasible region. And now, unfortunately, x1 becomes fractional again. Going back to our tree, we can see that at the left-hand side, we get a feasible solution. This solution is IP feasible, so it becomes our candidate solution to the original IP. No, we are not finished yet, but now we get a candidate solution, okay, here. And then this guy currently is fractional, okay? So that means we need to go further to see whether we can get anything that is better than this current solution. We're going to continue to that in the next video. Thank you.